Welcome to MEI Numerical Methods, Approximating Functions. In this video we're going to be looking at Lagrange's method. Lagrange's method is an alternative to Newton's method that we've just been looking at in the previous videos. It's generally more cumbersome, but it does have the advantage that it can cope with an h that isn't constant. So the x values don't have to go up by a regular amount each time. So as an introductory exercise, we're going to look at the equation of the line that passes through two particular points as shown there. So this is one of the standard forms for the equation of a straight line, and we've got both sides of the equation are expressions for the gradient. And this can be rearranged as shown here, and this is the final form we're aiming for. And the purpose of arranging it in this form is that we can see that when x equals a, we've got this term here is going to vanish, and the other term is just going to be, we're just going to be left with capital A. So that means the line goes through the point little a, big A, and then similarly for little b, big B. And we're going to extend this further shortly. So here we have Lagrange's formula, which extends what we've just been looking at for a straight line to a quadratic, and in exactly the same way we can see that if we put x equal to a, then both that term and that term are going to become 0, and the first term is just going to be capital A. So the curve passes through, the quadratic passes through that point, and similarly for the other two. So we're now going to apply this to a particular example. So we've got 3 points here: 2, 5, 3, 8, and 4, 13, and we're going to use the formula above to obtain a quadratic function that passes through those 3 points. And another thing we can use the function for is to do some interpolation to estimate the value of the function when x equals 2.5, for example. So plugging our values into the Lagrange's formula, we get that, and then with a bit of simplifying, or quite a lot of simplifying, we eventually end up with the quadratic x squared minus 2x plus 5. And if we're interested in the value of the function at a particular sort of interpolated point, 2.5 for example, then as with Newton's method, it's normally easier to plug it into the unsimplified version, or rather there's no need to simplify it, and so we get 6.25 for that. So we do get exactly the same results as we would for the Newton's interpolating polynomial, but generally speaking, the process is more cumbersome, but does have this big advantage that we can cope with an h that isn't constant. So that concludes the videos on the approximating functions methods.